Okay, so we're going to do problem 6.3. So in this problem, you're given the mass of Jupiter and the radius of Jupiter, and you're told a satellite is orbiting around Jupiter in a circle. So it's asking you how to find the orbital speed of the satellite. It gives you the answer, square root of g mass of Jupiter over r. And it tells you to use Newton's laws. So one of Newton's basic laws, F equals ma, and since this is a circular orbit, a equals v squared over r, so it's F equals m v squared over r, which is the radius. So the F, the force of gravity, is also, it's equal to g times, which is a constant, times the mass of Jupiter times the mass of the satellite over r squared. That equals the mass of the satellite. These are the mass of the satellite. V squared over r. So you can do some basic canceling. So that cancels, those r's cancel, mass of the satellite cancels. So you have gmj over r equals v squared. So take the square root of both sides, you get v equals the square root of gmj over r, which is what the answer is. So then in the second part of A, part 1, part 2, it asks you how to find the orbital period. So there's another basic equation where v equals d over t, but instead of using d over t, we can relate it to period with v equals the distance of the circle, which is 2 pi r, geometry, over t, which is the period, the time constant going around. So it's just big T. So it asks you to solve for t. So if you multiply by t and divide by v, you get t equals 2 pi r over v. And we solved for v in the last problem. So t equals 2 pi r over the square root of gmj over r. And I believe you can leave it like that, but the book has it in a different form. So if you square everything to get rid of this radical, you get t squared equals 4 pi squared r squared over gmj over r. Then divide that out. So t squared equals 4 pi squared r cubed over gmj. You take the square root, equals 4 pi squared r cubed over gmj. And I lied, you're not allowed to leave it like that because it tells you it looks like that. So that's how you get that answer. So in part B, it says the explorer wants the satellite's orbit to be synchronized with Jupiter's rotation. So basically it's asking you to determine the radius of this from this equation. So to do that, so you have t, from what we just solved, we have t equals square root of 4 pi squared r cubed over gmj, and we're looking for this. So again, if you square everything to get rid of that radical, t squared equals 4 pi squared r cubed over gmj. And then you put this on the other side, so r cubed equals gmj t squared over 4 pi squared. You then take the cube root to solve for r, so r equals the cube root of gmj t squared over 4 pi squared. And then everything else is plugging in, plug and chug. So the numerical value for g is 6.67 times 10 to the negative 11. Then the mass of Jupiter they give you, which is 1.9 times 10 to the 27. Then t they also give you, which is 3.55 times 10 to the 4th squared. That's over 4 pi squared. So you put that in your calculator, you plug and chug, you get r equals 1.59 times 10 to the 8th meters. C. So in C, they give you the dashed circle, J, Jupiter. It tells you that the satellite is getting interjected into the orbit at the desired value of p, but in part 1, the satellite is moving slightly faster than it needs to be. When it has a circular orbit like this, if you put it in faster, the circle is going to gradually get wider if it's going fast, and if you put it in slower, it gets slower and slower, and eventually gets very, very small. So in part 1, it says it's slightly faster, so instead of being this perfect circular orbit, the satellite will have an elliptical orbit that's bigger than the circle. And in part 2, it's the same Jupiter, same P, it says it's going slightly slower, so the satellite will again have an elliptical orbit, except it will be less than the desired perfect circle. And that's how you do problem 6.3.